cytochrome C will visit it's a mobile cytochrome, to the house number 4, and there is a very special type of cytochrome, and this cytochrome has also ferric form of iron. As soon as cytochrome C visits it, right, its ferrous goes back to ferric and electron is donated to last part of it. What is this? Ferrous. This iron converted into ferrous. Is that clear? And you know, there's a lot of juicy activity in this house number 4. Now, as soon as the iron of cytochrome present in complex number 4 gets loaded with the electron, right, now this cytochrome is capable of reacting with oxygen. Only this cytochrome here is capable of reacting with oxygen. So as soon as it gets the electron, right, what it will do, it will interact with oxygen, and suppose this molecular oxygen, this oxygen become highly reactive, and this oxygen will react with 2 protons, and both of them will convert into water. So the real activity, that electrons are transferred to oxygen in complex number 4. Electrons are transferred to oxygen in complex number 4, and reactive oxygen react with protons which are nearly available throughout the mitochondrion, right, and this will produce water and things will get wet. Am I clear? Any question up to this? So what really, do you have any question?
And then that one pumps hydrogen.
Pardon?
That one pumps hydrogen too, or protons into.
Yeah, protons are there throughout, because when Krebs cycle is running and other fuels are breaking down, protons are being removed, right? Now listen carefully. What is the name of this cytochrome, that cytochrome, and that one? This was cytochrome B, which was basing into house number 3. B for basing, it has a base in house number 3. Cytochrome C loves to see the thing here and there, so it's mobile, right? And what is this cytochrome? The last cytochrome is called A plus A3 cytochrome. A very special thing about this cytochrome is that not only it has iron, it has also copper. Not only it has iron, it has also copper. Is that right? Yeah? Yeah. So this is the last in the cytochrome system. So how many cytochrome we have seen playing a role here? Cytochrome B, which is based in house number 3. Cytochrome C, which likes to see the things right from house to house, especially house number 3 and 4. So this is mobile unit. Then cytochrome A plus A3, right, which is the last in the electron transport chain, and eventually this will interact with oxygen and unload its electron to the oxygen. So oxygen act as the final oxidant. Oxygen act as final oxidant. Now the names. What is the name of this? Who will tell me? This was shifting electron, look here, from Q to C. So it is called Q cytochrome C oxidoreductase. And the most important name which you should remember is the last one. What is the name of this? This is called cytochrome C oxidase. Cytochrome C oxidase. Any question here? There's no question here, right? Now, in a nutshell, just summarize it to put whole this thing in a bigger perspective. You remember that our main body fuels are carbohydrates, proteins and fat. Is that right? Now, from these, when you are catabolizing the proteins or fats or carbohydrates to produce the energy, right? Basically, you have to break their carbon skeleton and you have to remove the hydrogens. Is that clear? The carbon is removed in the form of carbon dioxide from the, when cells are producing energy, carbon is removed, carbon units are removed as carbon dioxide, and carbon dioxide shift from the cells to the interstitial fluid to the blood, and carbon dioxide is taken to the lungs and puffed out. Is that right? Then we are left with the hydrogen units. Hydrogen units from carbohydrate, proteins or amino acid catabolism are, most of those hydrogen units are transferred to the coenzyme NADH or to NAD and making NADH, or those hydrogens with their electrons are transferred to FAD to FADH2. In this way, from the major fuels of the body, during the catabolism, the electrons are transferred to the coenzyme NAD and coenzyme and FAD, and those coenzymes get reduced. Now NADH and FADH2, they will eventually unload their electrons to the electron transport chain present in the inner side of the inner mitochondrial membrane. The components of electron transport chain are complex number 1, complex number 2, then mobile unit, what is this? Coenzyme Q, complex number 3, mobile unit, cytochrome C, and complex number 4. The major player, the most important component of complex number 1 is NADH dehydrogenase in strong association with flavoprotein FMN. The major player in complex number 2 is succinate dehydrogenase with another flavoprotein which is FAD. Is that right? Then we said that electrons can transfer through this chain. NADH electrons are provided to the house number 1 or complex number 1. FADH2 electrons are provided to house number 2 or directly to the Q. Is that right? When electrons are added to the early part of the chain, they are highly energized. As the electrons go down the electron transport chain, they are progressively losing their energy. That energy is captured in a way for a special work. That special work is, as electrons are going down through the electron transport chain, protons are transported from the matrix to the intermembrane space. These protons will later on pass through the ATP synthase and result in generation of ATP. Is that clear? Out of this component, proton shifting occurs by complex number 1 and complex number 3, and also from complex number 4. If you are really curious, when electrons are passing, house number 1 in every event passes 4 protons here. House number 3 passes 4 protons there, and house number 4 passes only 2 protons there. Another thing, look, this is like an electron transport chain, and it can be interfered anywhere. Let's give you an example. Let's suppose if there is no oxygen available. Now this is a very important clinical situation. In many clinical situations, oxygen deficiency occurs to the tissue. If there is no hypoxia, if there is no oxygen available to mitochondria, and attention please, if there is no oxygen there, can cytochrome A unload its electron to this? So when it will convert into what? It will remain into reduced form. So when it cannot unload its electron, right? Can it accept the electron from earlier component? So it is just like blocking the conveyor chain. That if conveyor chain is moving, you stop it anywhere, then proximal to the block, all the luggage start backing up. So what really happens if oxygen is not there? What will really happen to the cells? If oxygen is not there, electron transport chain will stop here. Electron will accumulate here. Then electron cannot shift from proximal area. So all of it will remain loaded with electron. FM and H cannot come back and FMN is not available. So NADH will accumulate, and when NADH is accumulated too much, of course it will inhibit many steps of glycolysis and Krebs cycle, and energy production will stop. Am I clear? So when we say that oxygen deficiency, when there is oxygen deficiency, cells cannot make ATP. You have heard of it so commonly. What really happen at molecular level? When there is no oxygen to the cells or tissues, then mitochondria are not receiving oxygen. More truly speaking, the last cytochrome oxidase is not receiving oxygen, and electron cannot, oxygen is not there as final oxidant to accept the electron from the cytochrome A, A3 or cytochrome C oxidase. So all the electron transport chain, all the component proximal this and proximal to that are trapped into reduced form. Is that right? And electron transport chain does not run. Will it run? If there is no oxygen, electron transport chain is stuck. It does not run. Look, when electron transport chain will not run, protons will not shift. And when protons will not shift and accumulate into intermembranous area or space, then of course proton cannot move through ATP synthase. And when protons cannot move through ATP synthase, it's so obvious what will happen. ATP synthetase will not work, and phosphorylation of ATP will not occur, and ADP will not be converting into ATP, and cell will develop severe deficiency of ATP. Any question up to this? There is no problem. Now, we will continue. Another thing, there are different types of substances which can inhibit the electron transport chain. You can inhibit whole this chain at any step. For example, there is a substance which can block chain at this level. House number 1. Substance which will block the chain here, they are the toxic doses of barbiturate. Have you heard of barbiturates? These are the drugs, right, acting in central nervous system and suppressing the central nervous system. Barbiturates like amobarbitol or amitol. Amitol, or another substance is rotenone. So rotenone or amitol in very high concentration can block the transfer of electrons from complex number 1 to, what is this? To coenzyme Q, right? Another substances which can block the transfer of electron from house number 2, and this is malonate. Malonate can interact with complex number 2 and does not allow the FADH2 to shift its electron to the coenzyme Q. House number 1 blocked by amybarbital or rotenone, or house number 2 blocked by malonate. House number 3 or complex number 3 can be blocked by antimycin A. This can be blocked by antimycin A. Is that right? And the most important thing are the blocks at this level. You do not allow the transfer of electrons from cytochrome A, A3 to the oxygen. These are the most important and most dangerous. These are, can you tell me some? Have you heard of cyanide poisoning? Cyanide poisons. Cyanide react with the cytochrome and does not allow the cytochrome to interact with oxygen. So even if oxygen is there, but actually electrons cannot be shifted in presence of cyanide poisoning. This also happens in carbon monoxide poisoning. This can also happen with another substance called sodium azide. Sodium azide. Now these substances can bind with cytochrome oxidase and make it dysfunctional, and cytochrome oxidase cannot transfer its electron to the oxygen, so naturally it is stuck into reduced form, and then all proximal to this are stuck into reduced form, and further electron cannot flow through that, and of course protons cannot move from matrix to intermembranous space, and electromotive force is not developing, proton motive force is not developing into this space, and ATPase synthetase cannot be activated. Is it really clear? Right? At any level, when chain is blocked, look, for example, chain is blocked here, then all the components before the block are in reduced form, and all the component of electron transport chain downstream to the block are in oxidized form.
Is that like how antibiotics work, antimycin?
Yeah, but should not be considered antibiotic, it should be considered toxin for us.
Okay.
Right?
What's the name?
Antimycin A. Jill, do you have any question up to here? There's no question? Right. After this we come to a little more toxic activity. Now all these inhibitors, right, they are electron transport chain inhibitor. Is that right? Then another type of drugs are there which can inhibit phosphorylation. Let me make the phosphorylation unit here. You remember what is this I'm drawing? ATP synthase. ADP plus phosphate, and from here they fuse and release ATP. And of course you are so intelligent, you must be knowing that lot of protons were accumulated here, and these protons which were shifted to intermembrane space, you know, chemoosmotic hypothesis, when these protons were moving through this, right, ATP generation occurs. Is that right? But for this ATP generation, you know, most of the ATP is utilized in cytoplasm, and ATP is converted into ADP. Is that right? You remember that in energy utilizing different reactions in the cytoplasm. This ADP should come in, and this ATP should go out. Okay, we can make it like this, right? And for this reason, there is a very special type of transporter here, and this transporter is called nucleotide, adenine nucleotide transporter. This is also in inner membrane. It keep on bringing the ADP in, and whenever it brings one ADP in, it takes one ATP out. So for phosphorylation process, what are the requirements? Listen carefully. For phosphorylation process, number one, phosphorylation of ADP into ATP. Number one, we require proton motive force. There should be a lot of protons present in where? Intermembranous space. Number two, we should have a functional what? ATP synthase. And number three, we should have working adenine nucleotide transporter, because if everything is working but ADP is not coming in, can we make ATP? No. Now there are some toxins which work at this level. For example, you know, there is a hole in this, and through this hole, right, that has to go in, protons have to go in. There is a very naughty type of stupid type laughing, you know, toxin which stuck itself into that hole which is present in ATPase synthase. And if you give this toxin to someone, this toxin will bind into ATPase synthase enzymes, that component through which the protons move down, right? And do you think then this can move down? No. Can it rotate and can we make ATP? No. So this toxin is called oligomycin. What is the name of this stupid type of toxin is? Oligomycin. So naturally it is phosphorylation inhibitor. This compound is phosphorylation inhibitor. Then another substance is which is very much attracted here. Right? There's a substance which is very much attracted here and put its legs into this. And block the system. Very attracted here, I don't know what it's doing, but somehow it's blocked that transporter for ATP and ADP. And that compound is called atractyloside. Atractyloside, which is attracted to that ATP ADP transporters. Now these two compounds are an example that once they are there, right, they will inhibit the process of phosphorylation. We know one thing, listen carefully, that electron transport chain is an example of oxidative reactions. In the end, oxygen is oxidized. Is that right? Now listen, these oxidation reactions, truly called oxidation reduction reactions, but we call it, these oxidation phenomenon are coupled with what? Phosphorylation reactions. By accumulation of protons in intermembranous space. Again, listen carefully. This is very important statement that all the oxidation reactions in electron transport chain are coupled to phosphorylation processes of ATP, right, through accumulation of protons in intermembranous space. Is that clear? So these are coupled reaction. It's very easy to understand. If you stop, let me tell you. If you give an inhibitor to electron transport chain is not working. Will proton shift there? Will ATP will form? No. So oxidation is coupled with phosphorylation. Another example. If there is oligomycin or if there is a tractyloside and phosphorylation is not going on, attention please. For example, you have given oligomycin, then phosphorylation is not going on, or you have given this compound, ADP is not available, again this rotary will stop and phosphorylation is not going on. If phosphorylation is not going on, protons will accumulate here so much that can further proton come here? No, and electron transport chain will stop. So if you block the phosphorylation processes, oxidation processes automatically stop. If you block the, what is this? Oxidation processes, phosphorylation process automatically stop. So what I wanted to tell you that oxidation and phosphorylation processes are very tightly coupled. Is that right? So if you give the patient, again I will repeat it, if you give the person oxidation blocker, ATP won't be formed. Or if you give, or phosphorylation processes will be arrested. Or if you give phosphorylation inhibitors, what will happen? Oxidation process will stop. And now come the most important part of the lecture, where I don't know, in USMLE they make so many MCQs. That is the uncoupler. Those substances which uncouple the oxidative and phosphorylation processes. Because if you really have concept of those substances, it means you understand how these electron transport chain and phosphorylation ATPase synthetase is working together. Uncoupler are, normally they are very tightly coupled processes. Uncouplers are substances, look here, which produce proton leak. If there is some toxic substances which allow the protons unduly leak from intermembrane space to the matrix, right, then what will happen? That, attention please, when protons are unduly moving from intermembranous space to the matrix without passing through the ATPase synthetase, processes will be uncoupled. How they will be uncoupled? Look, when protons are moving here, ATPase synthetase will not be having protons going through it. So ATP synthesis will stop. right? ATP synthesis will stop or process of phosphorylation will stop. But as protons are moving here, they are not accumulating here, electron transport chain will keep on working. So electron transport chain keep on working, right? But phosphorylation stop, it means oxidation and phosphorylation processes are uncoupled. That one is normally when they are coupled, if one is active, only then other is active. If oxidation is inhibited, normally if oxidation is inhibited, phosphorylation will be inhibited. Or if phosphorylation process is inhibited, oxidation should be inhibited. Is that right? But uncouplers are really nasty. What they do, these are the substances which shift the protons from the intermembranous space to the matrix without passing through the ATPase synthetase, and oxidative processes become faster than normal and phosphorylation becomes slower than normal. And in this case, the energy is not utilized in formation of ATP, that is lost as heat. So such substances may produce high grade fevers. Those toxic substances which can disrupt or uncouple the oxidative phosphorylation reactions, they may produce high grade fever. One of those substances is salicylates, aspirin, very toxic levels of aspirin, salicylates. Someone has taken very high level of aspirin, normally aspirin is antipyretic, it reduces the fever, but in very toxic doses of aspirin you may develop the fever. Or many other drugs in very high toxic doses, right, they produce high grade fevers by disrupting the oxidative phosphorylation processes. You understand what is happening. That protons are being shifted from intermembranous space to the matrix without passing through ATP synthetase, so phosphorylation is inhibited. But because intermembrane space is very poor in proton, so electron transport chain keep on working very much and shifting lot of protons there which are leaking back, right? So in these patients, oxygen will be utilized too much, but ATP will not be formed, because utility of oxygen is a sign of oxidation. ATP formation is a sign of phosphorylation, ADP phosphorylation. So in these uncoupling drugs and toxic doses, they utilize, tissues use oxygen more, but they produce ATP less. Is that right? Another synthetic compound which is used as oxidative phosphorylation uncoupling enzyme substance is a toxic substance which act as special type of channels through which protons can move in. Actually, that is lipid soluble substance and it can bind with the protons and drag them in. There is a substance which is highly lipid soluble. It will bind the protons here and move down into matrix. This substance is called 2,4-dinitrophenols. 2,4-dinitrophenol, right? It also shifts the protons and act as an uncoupling agent. Is that right? Then another, under some circumstances when body really need to make a lot of heat, we need some physiological uncoupling proteins. You see polar bear, they go into hibernation. There are many animals which go into hibernation, but when they are coming back to, they are coming out of hibernation to active phase, they have to generate a lot of heat to warm up and then start their metabolic activity. For that purpose, those animals have a special type of protein here which is called this protein is called, yes, thermogenin. Thermogenin means heat producing proteins. Thermogenin proteins are present in inner mitochondrial membrane, and once these proteins are acting, they allow the protons to shift in, right? And in this way, they make the electron transport chain very active, and catabolism of food stuff, catabolism of carbohydrate and proteins and fats become very rapid with little ATP formation, and lot of heat is produced. Thermogenin. So these animals which hibernate for a long time, when they are coming out of hibernation, right before that, they produce a lot of thermogenins in their mitochondria, and these thermogenins, you can say, short circuit the oxidative process from ATP synthesis process, and a lot of heat is produced. A thermogenin proteins are also produced in the mitochondria of the brown fat. You know, human infant has small amount of brown fat, and the brown fat especially on the back, right, so that they can keep their back warm. I don't know how the nature has evolved us so wonderfully. You know, mothers, when they are breastfeeding the baby, they are holding the baby with their chest. So baby is warm from the front. On the back there is brown fat. Even though these days we don't use that brown fat mechanism, mothers are well resourceful and they keep the baby warm from every side. But fat on the back of the baby, interscapular fat, is brown fat. In the brown fat cells, adipocytes, there is a lot of mitochondria with a lot of thermogenin. So that thermogenin will short circuit and allow the protons to shift from intermembranous space to, what is this? Matrix, and uncouple the oxidative phosphorylation reaction. So in those mitochondria, electron transport chain runs very fast. A lot of, you can say, Stelco-A and Krebs cycle and other catabolic processes are going on. A lot of heat is being generated. Is that right? Is there any question up to here? Right? A few words about the mitochondrial diseases. Let's have a break first. Now a few words about mitochondrial diseases. Mitochondrial diseases will be discussed in detail in genetics lectures, but here we'll talk only few words. In the mitochondria, as I told you, mitochondria have many proteins, which are many enzymes and many transporters, right? For all these oxidative phosphorylation processes, mitochondria need about 100 polypeptide. Out of this, 13 polypeptide are made by mitochondrial genetic material, and remaining are provided by our nuclear genetic material. Right? So it means the mitochondria does not have a capability to synthesize all of its polypeptide, but still about 13 polypeptide mitochondria can synthesize on its own. Now, mitochondrial DNA has a higher rate of mutation. Mitochondrial DNA has a high rate of mutation as compared to eukaryotic cell DNA. You know why? Because when our DNA is replicating, there are special repair mechanisms. If there's a mistake, our DNA is repaired. But mitochondrial DNA does not have any efficient mechanism of DNA repair. So rate of mutation in mitochondrial DNA is very high. If there are severe mutations in mitochondrial DNA, the proteins which will be produced are mutant. And if mutant proteins are not functioning well, then mitochondrial oxidative phosphorylation processes are not very effective, and ATP generation will be reduced. Is that right? There are three different categories of diseases in which mitochondrial oxidative phosphorylation processes are impaired. One is called Leber's, right? One is called Leber's hereditary optic neuropathy. Leber's hereditary optic neuropathy. This is adult onset, bilateral loss, central loss of vision, right? This is inherited disease, Leber's hereditary optic neuropathy. Another disease is Mela's. This is mitochondrial encephalopathy. Remember, in mitochondrial diseases, those tissues which use a lot of ATP suffer most. For example, optic nerves use a lot of ATP in retina. They suffer severely in Leber's disease. In the same way, in Mela's, There's mitochondrial encephalopathy with lactic acidosis. Lactic acidosis. I hope you understand why. Because NADH from cytoplasm. Okay. And then stroke-like conditions. Stroke-like conditions. So in these persons, they develop severe encephalopathies, damage to central nervous system with lactic acidosis and stroke-like condition. And a third category which you are supposed to know is that is called myoclonic epilepsy. Myoclonic epilepsy. Again, it is due to damage to the central nervous system and red muscle fiber. Red fibers. Red fiber disease. What really happens that mitochondria are not working well in the red muscle fibers, right? And those muscle fibers are disrupted. And when you make histological section, they look like wavy and ragged. Is that right? So these are three mitochondrial diseases which you are supposed to know, right? Just their names. And as a general thing, you must know the mitochondrial rate of mutation is higher than our nuclear DNA mutation. And secondly, mitochondrial DNA, we require it properly functioning for some of the polypeptide which are part of the oxidative phosphorylation processes, and these three types of diseases are there. And last thing, mitochondrial diseases are inherited in a very special fashion. We call that maternal inheritance. What is the base of that? You know, the mitochondria which are working in your cells, Mr. Ostock, those mitochondria are coming from your mother or father? They are coming from your mother, not from fathers. Look, actually ovum is coming from mother and sperm is coming from father. Look, sperm has to do a lot of travel. You know, fathers travel a lot. So they put all their mitochondria together and make a special energy producing unit which is called middle piece of sperm. So all the mitochondria which are present into spermatogonium, mitochondria are fused together and made a very special powerhouse of energy, right, which help the sperm to travel a long distance from vagina to the uterus to fallopian tube, eventually reach to the ovum. Is that right? Right, this is suppose paternal genetic material, and here is maternal genetic material, and these are paternal mitochondria which are here and maternal mitochondria are here. Now what really happens at the time of fertilization, when sperm fuses with the ovum, middle piece does not enter into ovum. So paternal mitochondria do not contribute in zygote formation. The major substance is moving from the sperm to this is sperm nuclear genetic material. So you get 23 chromosome from father and 23 chromosome from mother and some other activating substances from the sperm, and now this fertilized ovum become activated, convert into zygote, and this fertilized ovum will go to 2-cell stage and then it will go to 4-cell stage and so forth. Eventually it will become a baby which will grow up and study in medical school. Now all the mitochondria which were present in oocyte, they have been inherited by, what is this? All the mitochondria which were present in oocyte, they are of maternal origin, they are inherited by the product of conception and the baby, right? So actually in all of us, in the boys as well as in the girls, these are maternal mitochondrions which are right now working in your cells and keeping your cells energy supply well. So your every cell is energized by maternal mitochondria. Paternal mitochondria do not contribute to that. What really fathers are contributing is no, not sperm. To you, I mean. Your father has contributed to you is his genetic material. That was nuclear genetic material. Father did not contribute to you his mitochondrial genetic material. So mothers provide you maternal genetic material, plus they're so lovely, they also provide you mitochondrial genetic material so that every cell is energized. Am I clear? If you keep this thing in mind, if maternal maternal mitochondria are defective, children are going to suffer. But if paternal mitochondrial genetic material is defective, children are not going to suffer. Let's have a look on a special type of pedigree. Let's suppose there is a woman and who is having unfortunately mitochondrial disease. This is a very pretty young woman, right? But unfortunately she has, suppose, Leber's atrophy. She's blind, but still someone, like in movies, falls in love with her, marries her, and she gets 4 children, 2 beautiful daughters and 2 beautiful sons. How many of them will have the Leber's atrophy eventually? All of them. That is the sad part. All of them will eventually develop. Because, why all of them? Because this was the unfortunate mother who is contributing her mitochondria to all the offsprings. Then somehow this is very loving family and somehow they get the lovers. This woman gets, this man, the boy gets a normal female and this girl gets a normal male. And now we have to see that out of the, in this pedigree, how many children will suffer? All of them, because defective mitochondria will come from mother side. We call it maternal inheritance pattern. But in this case, because even though this person is having mitochondrial defect, genetic defect, but he's marrying a normal female. The female is normal as far as mitochondrial DNA is concerned. Maybe she has some unusual thing, right? But anyway, this is their private matter. We will not interfere. So, but the thing is that he is marrying a normal woman as far as mitochondrial DNA is concerned, and this woman is going to give the mitochondria to all children. So, what will happen? All the children will be happy. And again, here you see what will happen. Disease will go to, yes, all of them. And here disease will go to none of them. The sad part, you can see that disease comes from mother to the all children, then from daughters to all children, and then again from granddaughter to all children. So this is the sad part of inheritance pattern in mitochondrial diseases. Is there any question? No, class dismissed. Welcome.